All right, so this is my last lecture, and I've used the first couple of lectures in this sequence to talk a little bit about several different problems in the world of applied probability that span a range of different areas. The first problem that I talked about was something from the world of Monte Carlo simulation, relating to what I called output analysis being that part of the simulation world that is concerned with trying to attach accuracies to your Monte Carlo computation, typically through confidence intervals. And in the second lecture, I talked about a set of problems that arise when you are concerned with trying to take Markov models and to use them in a predictive or prescriptive environment in which you really are concerned about getting the numbers right. And I argued that in that context, it's often going to be the case that the right models will have to exhibit time of day effects or day of week effects, in particular non-stationarities. And I talked about some of the tools available for handling those types of models. And today, in my final talk, I thought I would talk about something a bit different, a problem that I was introduced to more recently by one of my colleagues at Stanford, Ramesh Johari. So he works very extensively with different internet commerce platform companies like Uber, Lyft, and so forth. And there's a question that comes up in that context related to various types of experiments that these platform companies are undertaking on a constant basis. I'm going to say a little bit about that. And I'll talk about a interesting stochastic modeling problem that arises in that context, having to do with temporal experimentation. And as it turns out, that will connect nicely to using some mathematical ideas that are, I think, fundamentally important in the world of Markov chains, but aren't known probably as widely as they should be. And in particular, the most important of these tools that I'll talk about is Poisson's equation. So Poisson's equation, I think, is a fundamentally important concept in the world of Markov chains. And you'll see that by using Poisson's equation in a effective way in this class of problems, that you can get quite a nice solution to this temporal interference question. So that's basically going to be the goal of today's talk. So, by the way, this is joint work with Ramesh and also Ramesh's postdoc, Mohammed Rasuli. So I'm going to talk first of all about what temporal interference is, how it arises in the context of platform companies. Then I'm going to discuss some related mathematical ideas that I will use over the course of this talk, in particular Poisson's equation for Markov chains. And I'll say a little bit about Markov decision processes, in particular review some ideas from the world of Markov decision processes, the world of stochastic control for Markov chains, because I want to contrast some of the classical ideas that arise in that context with a control formulation that will arise in the setting of this temporal interference problem. And then I'm going to close with the main discussion point today, which is applying these ideas in the world of optimal adaptive Markov chain sampling, that being our solution to the temporal interference problem. So what is temporal interference? Well, all of the different internet commerce companies that one deals with on the web, all the different platform companies that one deals with on the web, and here you can see lots of different logos having to do with different companies that are playing in that space. All these companies are in a constant mode of doing experimentation, trying to understand how to deliver their product more effectively to their customer base. So you may have heard of this experimentation via the term A/B testing. So A/B testing I talked about a little bit earlier in this week. A/B testing is an environment where some portion of the incoming customers or some portion of the individuals interacting with the platform are going to get exposed to a new treatment. So for example, it may be that Amazon, for example, wants to do some experiment in terms of playing around with the ad format that they use or some sort of marketing incentive that they want to experiment with. And they'll take some randomized fraction of the customers that are interacting with their website, maybe on some afternoon, and some portion of them will get exposed to this treatment. So that's the standard A/B testing context where you can easily do a randomized experiment, and then you can compare the randomized group to the rest of the group, the control group, so to speak, and see if you get an improvement in performance through the treatment. So that's standard A/B testing. So let me now talk about a setting where when you engage in this kind of experimentation, you're typically going to have to implement this in a temporal kind of way, where there's no easy way to randomize. So for example, in the context of Uber and Lyft, these ride-sharing platforms, it might be that the company wants to experiment with some new surge pricing scheme that's intended to maybe induce some of their drivers to move from where they are currently into some part of the network where they believe congestion is going to be arising, let's say in the next half hour. So if you implement this type of experiment, now you're going to induce some portion of your drivers to move to some other part of the network. Now you can't continue running this experiment because it's an expensive thing to run. It may be that this particular experiment actually reduces revenue, reduces margin. It may be that it's a bad idea. And so typically you don't want to fully buy into this idea over an extended period of time. Rather, you want to limit the length of time over which you run this experiment so that the downside potential of running this experiment is limited. So that means that you're going to need to switch off the surge pricing algorithm at some point. And when you switch off the surge pricing algorithm, it's not like when you go back to the previous mode that the system has been restored to a state that's independent of the experiment that you did. So when you switch from going to the A mode into the B mode, maybe back into the A mode again, back into the B mode, every time you switch back and forth, temporally, there's going to be some final state to the system that the system ends up in at the end of an experimental phase. And now the next algorithm, let's say the B mode, is going to inherit that as its initial state in the next phase. And some of its performance is going to be adversely impacted as a consequence. So this is what's called temporal interference, this idea of having to switch back and forth between one mode of experimentation, an A mode, back to a B mode, is not something where you have unbiased randomized samples available. Rather, you have some correlation effects that are induced by switching from one mode to the next. Okay, that's the issue of temporal interference. Each algorithm's action changes the state as seen by the other algorithm, and that induces bias. So what the standard practice is these days is something called switchback designs. Switchback design is exactly what it sort of suggests. You just switch back and forth between, let's say, the A mode, the B mode, the A mode, the B mode. And again, the problem is that every time that you switch back and forth between one experiment A to the alternative B, back to A, back to the alternative B, the final state that is induced by use of this experimental algorithm over this interval of time is the initial condition inherited by the algorithm B over the next phase, and that sort of creates a situation where it's very hard to cleanly compare the performance of algorithm A to algorithm B. So what we'd like to do is to somehow create a theoretical platform, theoretical framework for thinking about how to create better algorithms that can reduce the amount of temporal interference present in doing these types of experiments. So a quite natural mathematical framework for thinking about this class of problems is to think about the platform state as being represented through some Markov chain. So, and now what happens is that when you run the A design, basically that induces transitions from one state to another associated with use of that particular algorithm. There's one transition matrix that governs A experiments, another transition matrix that governs B experiments, and somehow what we're really trying to compute, really trying to estimate, is the effect of what would happen if we used the A design over the long term versus the B design over the long term. So what we'd really like to be looking at is what's the treatment effect in using A versus B when the treatment is going to be applied over a very long interval of time. In particular, is going to involve looking at the equilibrium characteristics of running that algorithm over a long time interval. So we're thinking about an experimental situation where we're switching back and forth between A and B, and yet the quantities that we're trying to estimate as treatment effects are equilibrium values under the two different models, the two different dynamics. All right. So what we'd like to do is we'd like to consistently estimate that equilibrium difference in treatment effect. And what we're going to be talking about is a Markov policy for doing this allocation, for switching from A back to B. That in some sense is an optimal policy. We're going to characterize that optimal policy and look at some of its basic characteristics. Now that optimal policy is going to be something that is derived using these mathematical tools that I described earlier, in particular Poisson's equation and some ideas from the world of MDPs, Markov decision processes. Okay. So now let me talk about these related concepts. So first of all, Poisson's equation for Markov chains. What is Poisson's equation for Markov chains? Well, I'm going to discuss it in its simplest context, namely that of a finite state Markov chain. So we have a Markov chain Xn evolving according to a transition matrix P. The xy's entry is the one-step transition probability of going from state X to Y. And Poisson's equation involves solving this equation for a given right-hand side F. As usual in the world of Markov chains and Markov processes, we think about functions on the states as being encoded through column vectors. So our right-hand side here is a function, a column vector F, and we want to solve for the function G, the column vector G that satisfies the linear system P minus the identity times G equal to minus F. And of course, we recognize that because this is a stochastic matrix P, one is an eigenvalue of a stochastic matrix P, that means P minus the identity is a singular matrix. That means we have some difficulties potentially in solving this linear system, some things that we need to think about. And in particular, because of the fact that this is singular, we can't solve this linear system for all possible right-hand sides. There needs to be some solvability condition that has to be imposed. And the correct solvability condition is, well, this is a finite state Markov chain. I'm assuming it's irreducible. It has a unique equilibrium distribution pi. And it has to be the case that this function on the right-hand side has equilibrium mean equal to 0. In other words, if I encode the equilibrium distribution pi as a row vector, and I take the inner product of that row vector with the column vector F, pi F is equal to 0. That just is saying equilibrium mean of F is equal to 0. Now, why is that solvability condition necessary? Well, you can see from this equation, if you just take this row vector pi and I hit both sides of this equation with pi, I get pi p minus pi over here on the left-hand side. That has to vanish. That means on the right-hand side, I have to have pi F equal to 0. So that's the obvious solvability condition. Now let's proceed under the assumption that I have pi F equal to 0 on the right-hand side. So another characteristic of this linear system is, well, we know that, again, since P minus the identity is singular, I can't solve this linear system for all possible right-hand sides F. Also means that, in general, I'm not going to have uniqueness of this solution on the left-hand side. And of course, the sense in which this thing doesn't have a unique solution, it's actually quite easy to describe the sense in which this linear system doesn't have a unique solution. In particular, if I take the function g, any solution to this linear system g, and I add on a constant vector onto that solution, Then because of the fact that P has row sums equal to 1, that will not, it will still be the case that G plus that additive constant function will be a solution of this linear system. So this thing is always never going to be unique. It'll only be unique up to an additive constant. All right, so now again, let's go back up to this linear system, P minus the identity times G equal to minus F. And I claim that if I can find a solution G to this modified linear system here, it will necessarily satisfy Poisson's equation. Now let's see why that's the case. Capital Pi, by the way, is the matrix in which all of the rows are equal to the equilibrium row vector little pi. Now, I claim that if G satisfies this system, it satisfies the one up here. You just take pi of both sides of this equation. Again, pi times P minus the identity is equal to 0. So this contribution vanishes on the left-hand side. I have pi f equal to 0 on the right-hand side. That leaves me with pi g equal to minus pi f, but pi f is equal to 0, so pi g is equal to 0. So this term is actually 0. But I didn't add anything on by putting the pi g in there. Okay, so any solution of this is a solution of Poisson's equation. And the nice feature in terms of writing it in this form is that now I have a coefficient system on the left-hand side that looks like I minus some matrix B, the matrix B in this case basically being P minus pi. And that P minus pi has a nice property. In particular, if I take P minus pi to the nth power, that sequence of matrices will converge to 0 as n tends to infinity. And that is just a consequence of the fact that if I take P minus the rank 1 matrix pi, and I take this to the nth power, well, let me just do this for the case where n is equal to 2. That will illustrate the general point. I get P squared minus pi p minus p pi plus pi squared. Now, because pi is the equilibrium distribution for the Markov chain, it satisfies pi p equal to pi. That translates in this matrix world into saying that this thing has to be equal to minus pi. Now what about p times capital pi? Well, this is a rank 1 matrix. All of the rows are identical. All of the column entries in a given column are one and the same. Again, if I look at the xyth entry of this matrix product, that'll be the inner product of a row of p with a column of pi. That column of pi has a common entry coming down that column. That can be factored out of this inner product sum. And as a consequence, I get that common factor in the inner product sum multiplied by the row sum of p. The row sum of p is 1. That basically is saying that p times pi is another pi. Now for the same reason, pi squared is just pi times pi. That's a stochastic matrix times pi. That again, through the same reasoning, has to be a pi. So I have this. And so what this translates into is just p squared minus pi. And in the general case, I have p minus pi raised to the nth power equal to p to the n minus pi whenever n is greater than or equal to 1. All right, so I claim that this goes to 0 as n tends to infinity. That's just a consequence of a very basic result that all of us know about irreducible aperiodic finite state Markov chains. It's always the case for such Markov chains that there's a loss of memory in the system in the sense that the n-step transition probabilities converge to the equilibrium probabilities at n goes to infinity, which translates in the matrix context I've written here to p to the n minus pi going to 0 as n tends to infinity. So that means that this geometric sum on the right-hand side does indeed converge, and that it goes to 0. It actually has to converge at a geometric rate as n goes to infinity to 0. So there's a convergent sum. That means that I can define the inverse of I minus p plus pi through this infinite sum. So this inverse, matrix inverse, always exists. This matrix inverse is what's called the fundamental matrix. So the proof that I just gave was a proof that depended on loss of memory. But if you do a slightly more nuanced proof, you can also extend it to the periodic irreducible Markov chain context. And so in general, when you have an irreducible Markov chain, this matrix inverse exists. Fundamental matrix exists for any irreducible finite state Markov chain. Okay, so now we're going to use this fundamental matrix. And let me illustrate how you can use this idea in the context of proving a very basic result in the world of Markov chain theory, namely the law of large numbers for Markov chains. So now we have some function f of x defined on the states of the Markov chain. We want to prove that the average of the f of xj values converges with probability 1 to the equilibrium expectation. So this is standard, plain vanilla law of large numbers for Markov chains. So the way that we're going to attack this is by trying to write this quantity in terms of a martingale. So in particular, obviously when we look at proving this result, one way of establishing this is just bring the right-hand side over the left-hand side. And then if you simplify the left-hand side that you get as a consequence, you'll have a numerator divided by n. The numerator is obviously going to take this form. So let's write that numerator in terms of a martingale. So what we are going to do is, let's see, what have I done here? Should I do yes or probably not? Okay, so what we're going to try to do is write this thing as a martingale. That's where Poisson's equation plays sort of a critical role. Thank you, Sandeep. So in terms of writing this as a martingale, we'll solve Poisson's equation for the centered function f of x. So you take f of x, subtract off its equilibrium expectation, call that function f sub c of x. The c here sort of representing the fact that it's a centered functional, centered by the equilibrium mean. Now we try to solve the linear system p minus identity times g equal to minus fc, and notice that since f has been centered, this fc satisfies the solvability condition for Poisson's equation, namely it has equilibrium mean equal to 0. Okay, so now we have our solution to, we have our Poisson's equation. We know through the fundamental matrix that that Poisson's equation has a solution. So it has a solution G. And now let's note that if we take the conditional expectation of g of xi given the history of the Markov chain up to time I minus 1, that is just going to be the sum over all probabilities from the current state xi minus 1 of the probability of going to the next state y. That's given by the transition probability pxi minus 1 to y multiplied by g of y. So one-step conditional expectation involves this quantity, which of course can be represented in terms of the transition matrix P and the column vector G, or the function G, as PG evaluated the xi minus first state. So as a consequence, since I have computed here the conditional expectation of g of xi, and if I subtract off the conditional expectation of g of xi from g of xi itself, well, that's the standard way of computing, a standard way of basically building a sequence of martingale differences. So di equal to g of xi minus pg of xi minus 1 is a martingale difference. So that means that if I sum up these di's, I have a martingale. Now let's see what this martingale actually looks like. I've just plugged in what the di's are, g of xi minus pg evaluated at the previous time step I minus 1. And now let's begin doing some rearranging on this second term here. The second term here with an index I minus 1 is basically summing the pg's from index 0 up to index n minus 1. And then I'll just attach all of the indices between 1 and n to their corresponding g of xi's. There are a couple of unmatched quantities, and in representing this sum as this sum down here, the unmatched quantities, at least one way of creating the unmatched quantities is I've got an extra g of xn in this sum that isn't represented down here, so I have to add that back in again. And this term down here has an extra term in it, a g of x0 that isn't represented up here, so I have to subtract that off. And now it's at this point that I can use the fact that g minus pg is the solution of Poisson's equation for fc. So this thing right here is just my f sub c of xi's I have my g of xn, my g of x0, and now I have my martingale representation of this additive sum. So now we're basically almost done with getting the law of large numbers. I have this sum represented in terms of martingale divided by n, plus a couple of end effect terms divided by n. I have a finite state Markov chain, so clearly since the G is bounded over a finite state space, each of these terms goes to 0 as n goes to infinity. Now the question is, how does mn over n behave? And of course, there are lots of results from martingale theory that tell us when a sum of martingale differences, mn divides by n. So you just apply one of those martingale results, and voila, you have the law of large numbers for the averaged function values up to time n. So that's an illustration for the law of large numbers. For our purposes, we're going to be looking at trying to compare estimators and trying to compare the quality of estimators. Comparing the quality of estimators is typically going to mean that we want to compare variances of the estimators. An estimator is better than another estimator if its variance is smaller. So we now want to go from a law of large numbers environment to a central limit environment where we can look at the variability of the quantity. So let me do that next. So we're basically at a point where we can also easily get a central limit theorem for a Markov chain by virtue of that martingale representation. And now instead of dividing by n, I'll divide by root n. Exactly the same principle as before. It says that these end effect terms goes to 0 as n goes to infinity. And now we're going to get a central limit theorem for these centered functionals, for these centered function values, provided that mn over root n converges to a normal as n goes to infinity. And again, standard application of martingale central limit theorem. There are a zillion of them in the literature. Apply any one that you wish. They'll certainly apply in this very simple, easy context. And as a consequence, we discover that this set of centered function values does indeed converge to a normal, where that normal can be expressed in terms of the variance of the martingale differences, in particular the variance under the equilibrium distribution pi of a martingale difference, and that just computes out to be this quantity down here. Right? So now we have a nice representation of the variance of this sum of function values from the Markov chain, expressed in terms of the solution to Poisson's equation by applying this martingale central limit theorem argument. So there are lots of other applications of Poisson's equation. It's, I think, one of the most fundamental ideas in the world of Markov chain modeling. We'll see a little bit later that Poisson's equation also comes up implicitly in the world of average reward or average cost stochastic control. It comes up quite naturally in the setting of looking at gradients of equilibrium expectations. So gradients of equilibrium expectations come up in many different applications environments. In particular, if you have a Markov chain, depending on a set of decision parameters, you want to optimize the performance of that Markov chain over the set of decision parameters that are available to you. Very natural formulation of that is to look at average reward per unit time or average cost per unit time to try to optimize that. That means that if the decision parameter is a continuous parameter, we're going to try to perhaps optimize it numerically by computing gradients. That means that we want to be able to compute the gradient of this expectation easily from a numerical standpoint. And let me just point out how Poisson's equation comes up in this context. So in particular, we have a Markov chain having a transition matrix that depends on our decision parameter. That means, obviously, the equilibrium distribution that goes with that transition matrix will depend on that parameter. The defining equation for pi of theta is obviously the standard defining equation, the standard stationarity equations for the Markov chain. This will hold for every value of theta. Assume that p of theta is smooth. That should imply that pi of theta is smooth. Now let's differentiate both sides. We're just applying the product rule. Now bring this term with the pi prime to theta here over to the left-hand side. And what we see is that the gradient of pi of theta involves solving this equation. And this is basically just a measure-valued version of the Poisson's equation that I discussed earlier. So there's a function version of Poisson's equation. That was what I discussed a couple of slides ago. And here's the measure-valued version of Poisson's equation with pi prime of theta now being in general a signed measure. Okay, so that's the gradients of the expected value. Now, if you go back to the discussion that I gave yesterday about modeling of non-stationary Markov chains, I also talked about approximations that are available in that context. And the approximations that I looked at were approximations in settings where the transition probabilities were changing slowly as a function of time. And I wanted to look at first order asymptotic improvements to the pointwise stationary approximation that take into account changes in the transition probabilities. And we found out that in the presence of smoothness, there was a way of systematically deriving these first order asymptotic improvements to the pointwise stationary approximation. In the slowly changing case, it's going to be the case that the transition probabilities are small perturbations of the transition matrices at neighboring times. And that means that we can think about the transition probabilities changing as a function of time according to some small perturbation. That means that in turn, again in that context, it should be the case that the perturbed transition matrices can be expressed in terms of derivatives. And now, again, somehow you implicitly come back to Poisson's equation through an argument that looks similar to this. And if you go back and you look at the equations that were derived in yesterday's lecture, they indeed, in particular in the context of looking at the pointwise stationary approximation, are exactly the Poisson's equation that arises in this context, right? So here are at least three different settings in which Poisson's equation arises as a fundamental tool that go beyond the law of large numbers and central limit theorem that I've mentioned a few moments ago. All right, so the second thing that I want to just talk about a bit is to talk about Markov decision processes. So let's suppose that I want to compute an optimal policy, an optimal control, minimizing the long run average cost of running some Markov chain. So the xj's are the states of the Markov chain evolving over time. The aj is the action taken at time j. aj will be an adapted policy. It has to depend only on the history of the Markov chain up to time j. Can't be clairvoyant. Now the optimality equation that comes up in this context for the value function is v of x plus gamma equal to the minimum of the costs on the right-hand side plus the sum of the transition probabilities p sub a of x y against v of y. So that's the standard Bellman equation, HJB equation for this particular control problem. And now you can actually sort of see that Poisson's equation is actually hiding in here. So in particular, if you think about what this equation is representing for the optimal choice of action, I have the optimal, let's say, A star sitting here. For the optimal A star, I can drop the minimum. The right-hand side is attained by C of x A star plus the summation over y of the P of A star xy times V of y. And now this looks like Poisson's equation. If I just bring the V of x over to the right-hand side, I bring the C of xa over the left-hand side. That's exactly the Poisson's equation that we've been discussing just a few moments ago. So Poisson's equation is sitting implicitly in this when you specialize the right-hand side to the optimal policy. Now, this particular value function, this particular optimality equation, one way of trying to compute v of x is to try to represent v of x as being the solution to a linear programming problem. And this sort of standard way of getting a linear program out of this optimality equation is just to recognize that since the v of x plus gamma is the minimum of everything here on the right-hand side, that means in particular that v of x plus gamma is greater than or equal to each one of these right-hand sides as a function of a. So for every choice of a, you get a linear inequality over here. So you now get a whole bunch of linear inequalities that the v function has to satisfy. And then if you impose the right a linear objective function in this problem, you'll recover the v of x. Now there's a dual to that linear program, and the dual to the linear program is here. There's a very natural alternative way of representing the solution to this stochastic control problem. Namely, we're going to think about randomized controls. Pi of xa is going to be the fraction of time that we end up in state x under the optimal control and choose to use action A while in state x. So these are so-called state action frequencies. And what we want to do is minimize the long-run average cost per unit time. That's given by this sum. And then the state action frequencies are going to have to satisfy equations very similar to the equilibrium or stationarity equations for an uncontrolled Markov chain. And that gives us this system of linear equalities subject to the pi of xa's being a probability distribution on the product space of states and actions. So here's the admissible set of state action probabilities. That's going to be some nice polyhedral set characterizing the pi of xa's. And this is something I am pointing out here because we're going to see that exactly the same polyhedral set is going to play an important role in this temporal interference context that I described at the beginning of this talk. By the way, you recover the optimal policy in this case by just choosing an action A in state X according to these pi of xa divided by the normalized pi of xa primes. Now, by the way, in this particular context, we expect the optimal control to be non-randomized. We don't have to do any randomization in this context. And in this particular setting, in great generality, it'll turn out that this polyhedron has extreme points. And in particular, this function is minimized at an extreme point at which this pi of xa basically describes a deterministic control. In particular, there'll be only one state and one action A for which pi of xa is positive. Okay, so now let's apply these ideas in this temporal interference context. So again, we're going to be building a theoretical framework in which we have a finite state space S. We have two algorithms, 1 and 2. We have two different transition matrices describing the behavior of the system under the two different treatments that are available. And we have equilibrium distributions pi of 1 and pi of 2 for each of the two that corresponds to each of the two transition matrices. We have rewards available both under the first action and the second action. So there are R of Lx's. And at time n, we're going to be in state n. We're going to choose an action an, and we'll get a reward Rn as a consequence. So what's the treatment effect that we're going to try to estimate? It's going to be an equilibrium reward difference treatment effect that we're going to try to compute. And that, of course, is just going to involve averaging the rewards under one treatment 2, let's say, against the corresponding equilibrium probabilities for treatment 2, and subtracting off the corresponding quantity under treatment 1. So that's just this simple difference of two inner products. We get to choose an estimator and a policy. So the estimator, I'll talk about in a moment. The policy is going to be some sequence of adapted ANs. I have a history up to time n. I have to make a decision about whether I continue using, let's say, treatment 1, or whether I switch over to treatment 2. So at every time, I make a decision about which treatment I'm going to use in the next time period. So those are the ANs. The ANs are either 1 or 2. All right, so the gamma n of x, L of x's are going to be the empirical fractions of time that I am in state x and I applied treatment L in that state. So just the long run, the number of times that I've chosen action L in state x. The Rn of L x's will be the rewards that I pick up over those transitions in which I applied action L in state x. And then I'm going to also be estimating transition probabilities. Now, why I'm going to be estimating transition probabilities? I don't know anything about the structure of my Markov chain, so I'm going to treat this problem as a non-parametric statistical inference problem. So I'm going to be estimating all of the transition probabilities non-parametrically, and my Pn of Lx, Ys are the non-parametric estimators for the transition probabilities in this context, namely the probability that I go from X to Y at a given time, given that I chose to use treatment L in that time period. So these are just the empirical frequencies of jumping from X to Y over those time steps where I chose to use treatment L. So then I'm going to get, when I've sampled for a long period of time, I'll have a non-parametric estimate for the transition matrix P of 1, another non-parametric estimate for the transition matrix P of 2. Now, the obvious way of estimating the equilibrium distributions under these two non-parametric estimators is just to compute the equilibrium distribution of the non-parametrically estimated transition matrix, right? So we have a P sub n of, let's say, treatment 1 or state xy. I have a whole matrix of these estimated transition probabilities. And in the world of maximum likelihood, when you have a maximum likelihood estimator and you want to compute some function of the parameters, estimate of some function of the parameters of the underlying model, the MLE for that function of the parameters just is plug in the estimated MLE into that function of the parameters. So if I want to estimate, in the world of maximum likelihood, if I want to estimate G of theta, what I should use is just compute my MLE theta hat and just use G of theta hat as my MLE for G of theta. So in this context, you can think about the equilibrium distribution as being a function of the transition matrix. If you apply this particular paradigm in this context, that suggests that if I want to estimate pi of theta, well, pi of theta is a function of the transition matrix. What I should just do is compute the equilibrium distribution of the estimated transition matrix. So that's what we're going to do here as our non-parametric MLE for this problem. So pi n of 1 is the non-parametric MLE for the equilibrium distribution under treatment 1. So I have that for treatment 1, I have it also for treatment 2, and now I'm going to estimate the treatment effect by looking at this difference. So that's the obvious thing to do. Now I'm going to make a bit of a mathematical restriction. I'm going to assume that the adapted policies that I'm looking at are what I'm going to call time average regular, which means that the long run fraction of time that I use action L in state X, I use treatment L in state X, converges to some limiting probability where these gamma of Lx's could potentially even be random. So I'm going to assume that these limiting fractions exist. That's what I call time average regularity. And then the limits that I have over here, I'll call that the policy limit. So it turns out that for any time average regular policy with strictly positive policy limits, you can get a nice central limit theorem for the treatment effect. And here's what it is. It involves a normal random variable on the right-hand side. Well, not quite a normal, standard normal random variable. You'll notice that the gamma I of x's are appearing here on the right-hand side. Let's just remind ourselves of what these things are. These are the policy limits that are arising in this context. I am allowing the policy limits, just in terms of being more general, to be random. And so these quantities on the right-hand side involve not just normals, but also random factors, gamma of 2x, gamma of 1x sitting over here on the right-hand side. These gamma I of x's are independent of these two normals. That's something that you quite often see in looking at the martingale central limit theorems, is that the right-hand side of the martingale central limit theorem is often a randomized limit. That has to do with stable convergence theorems in the world of martingale central limit theory. All right, so what are these sigma squared L of x's that are appearing here? We know what these things are. These are the time average limits. These things have to do with, maybe not too surprisingly, given the martingale central limit theorem approach that we used to the central limit theorem for Markov chains, these things involve the solution to Poisson's equation for the Markov chain. These things are coming out somehow of that martingale difference representation that I discussed earlier in the world of the CLT for Markov chains. And as usual, here's the fundamental matrix that we discussed earlier. So the G tilde of L can be represented in terms of this for each of the two Markov chains and their corresponding reward functions R of 1 and R of 2. And now, let me just go back to this. We're looking for an optimal policy. An optimal policy basically is going to translate into optimal choices of these policy limits. Remember again that I am restricting myself to time average regular policies. So asymptotically, these policies are characterized by the gamma L of x's. So the decision variable in this context, the optimal choice of policy is going to involve an optimal choice of these gamma I of x's. And so the question is how to optimize our choice of these. Well, if you want to optimize a choice, we have to have some feasible set. The fact that these policies are time average regular means that it's simple to prove, just as in the world of standard MDPs, that the limits have to be sitting inside the same polyhedron that we had in the context of average cost, average reward MDPs. So the gamma I of x's have to be sitting in this polyhedron. And that means if we just go back to computing the variance of this right-hand side, the variance of this right-hand side as a function of those policy limits is given by this quantity. The policy limits have to be sitting inside this polyhedron. And now we have a very nice convex optimization problem to solve relative to this linear polyhedral constraint. So it's a remarkably elegant, at least in my view, a remarkably elegant, simple solution to this problem. It looks a lot like the standard world of MDP optimal control, except in this context, we don't get a linear objective when we look at trying to compute the optimal policy. What we have instead is a convex objective function. So this theory is telling us that at least in terms of optimizing over the class of policies that, for example, are stationary Markov policies, the right way to do this is by minimizing this convex objective subject to the time average limits belonging to this polyhedron. Assuming that we knew what all of these quantities were, what the pi I of x's were, what sigma squared of I of x was, that would be something that an oracle would know. So the oracle would know all of the data in this thing. We could optimize this, the oracle could optimize this, and the oracle would tell us that we should use this particular optimal policy, the p star L of x's, the fraction of time, the probability that we should choose action L in state x is given by the same type of quantity as we see in the standard MDP context. It's in general going to be a randomized control because virtually always this convex optimizer is going to be minimized in the interior of this polyhedron, so it'll be a truly randomized policy in general. So this policy minimizes the asymptotic variance of this estimator. And let me just say a little bit about the fact that having two Markov chains running actually allows us to do more effective exploration in many examples than just having a single policy. So you can see in this particular context that you have the red transitions corresponding to, let's say, treatment 1, the blue transitions corresponding to treatment 2. And you can see that it might be that you're very interested in sampling these particular states down here. Maybe the rewards are high in these states down here. Because of the fact that you have cyclic structure in the way this Markov chain operates under each of the individual chains, if we switch back and forth from chain 1 to chain 2, we can switch from we can first of all go in the right direction using the red chain, Once we're done with sampling 1, 2, and 3 down here, now we switch back to the blue chain. We use blue chain dynamics to go back the other way. And now we can do lots of sampling just going back and forth over these states that would not be possible using the transition structure of either chain 1 or chain 2. So this is indicating a significant loss of efficiency that you can have in many settings as a consequence of using, let's say, one chain for an extended period of time, then another chain for an extended period of time. That's sort of the standard default practice these days in the way that switchback policies are implemented in the context of temporal interference. So there's lots of efficiency that is lost when you run your policy in that switchback way. So the outline of the argument, there'll be a couple of dimensions in which Poisson's equation comes up. So if you look at the pi n of i's that I described over here as being the non-parametric MLEs for the equilibrium distributions, they actually will satisfy this equation. And now you can see here on the left-hand side, this is looking very much like something coming out of Poisson's equation. You have the coefficient system that looks like I minus p plus pi. That is pretty much exactly the coefficient system that comes up in the context of Poisson's equation. Let's see, exactly, yes. This should have been a rank 1 matrix. It should have been a capital pi. Yeah, this is a row vector, this is a matrix. Exactly right, thank you, Remco. So here's Poisson's equation coming up when you bring the inverse of this matrix over to the right-hand side. And when you look at these differences of the Pn of i's minus p of i's hitting these solutions to Poisson's equation, these g of i's, it's easy to, very simple calculation to show that these things are basically going to be martingale differences involving the solution to Poisson's equation. And when you have martingale differences, that makes variances very easy to compute, which is basically why you get this very nice variance decomposition appearing in that central limit theorem. This is a pretty easy policy to actually implement. Obviously, in the real world, we don't know what the actual transition probabilities are. We don't know what the pi of i's are. We don't know what the solution to Poisson's equation is. But we can estimate all of these things. So in the real world, we have to estimate things in order to actually, let me just point out, and actually, in order to be able to compute the solution of this thing, we actually have to estimate pi squared of Lx, sigma squared of Lx adaptively. And as often is the case, we can always be unlucky in terms of the way we do adaptive estimation. It may be that we get unrealistically optimistic estimates of some things as we do the adaptive estimation. We need to do some forced exploration also as a function of time. There are lots of ways of doing it. This is just one algorithm for inducing forced exploration so that we explore all the different policy alternatives before discarding them. And when you do that, you got an implementable optimal policy that achieves the best possible under the class of policy actions that I've described in this talk. The analysis easily extends to random rewards. And so what we've done here today is we proposed a benchmark model, a Markov chain model to look at switchback issues and to sort of understand better what an optimal, truly optimal policy would look like. This is something that, at least in principle, could be applied in the context of looking at temporal interference. And Mohammed Rassouli, the postdoc, has actually gone out and talked to a bunch of companies in Silicon Valley about use of this type of policy in the context of temporal interference environments. And it actually looks like there's quite a bit of interest in applying ideas along this particular path. So something that potentially could have some impact in terms of this class of issues. There are a bunch of different ways in which it could be extended. You could look at finite horizon versions of this. After, obviously in general, we don't actually have an infinite amount of time to explore and to understand what a good policy might look like. It may be that you need to make a decision the next week. How would you look at finite horizon issues? It could be that you have more than one treatment that you want to look at, multiple treatments. And you could also have a situation where you have some non-stationarity effects, as always. So I pretty much finished the talk on time. Okay, thank you very much.